This video is the result of the last few weeks of my study of gravity and its relationship to energy and its relationship with the universal gravity constant G. And you may like to get a copy of this chart, which you can't read very well here, of course, but it's on the Father Physics website, fatherphysics.com website, and you may be viewing this video from YouTube. So if you go to fatherphysics.com, you'll find both this video and also this chart, which is a spreadsheet which shows for the planets and for the moon calculations of their initial orbits and when they were first created, on the assumption that the planets all came from the sun, or at least most of them, and they're all shown as or calculated that way, and also that the moon, which we know came from the Earth, or directly from the Earth as a result of an asteroid, or which I think was a would-be planet from the sun that struck the Earth and caused the moon to be formed. But this diagram, or this chart, which is self-explanatory, I think, I will be going over it later on. But if you look at that, you'll see that I've used this to do some calculations to find the value of G, the universal gravity constant. So I take that down now and discuss what an analysis of the universal gravity constant has produced. Now, we all know Newton's equation, which is that the force of gravity is equal to the sum, or product rather, of the masses of the two bodies involved multiplied by the universal gravity constant G and divided by the square of the distance between the two bodies. I use a uppercase R because it's easier to distinguish from a V and other signs. And the acceleration, which is equal to the force divided by the mass, is equal to simply the mass of the body, such as the sun, the central body, times G and divided again by R squared. Now G is interesting, and first thing I want to show is that it's not really a natural constant as C and Planck's constant H can be considered natural constants. You see, C is simply the ratio of a single natural unit of length, a quantum of length, divided by a natural unit of time. It's the natural velocity for which anything can travel, which is 1 unit of space in 1 unit of time. Planck's constant is a unit of energy times a unit of time. But G is more complicated. It has the dimensions of length cubed divided by mass divided by the square of time. And this is quite a complicated constant. And if these were natural units and the value of it would then be 1, as it is in the case of Planck's constant and the speed of light. If for this bit to be 1, the only interpretation we can give to this is that it represents the rate at which a single unit of mass is increasing in volume exponentially at an increasing rate. And that's a very interesting, although it seems unlikely, but it's very interesting because it exactly describes Einstein's equivalence principle, which more or less says, although he didn't describe it this way, but it more or less says that by standing on the ground and feeling the force of gravity downwards, you could be experiencing instead and could not distinguish between that force and the fact that the Earth is accelerating upwards at 32 feet per second. There's no way to distinguish between the two. And that's the equivalence principle. He described it as being in a box with a rocket, but it's the same thing. So it could mean that, and if it does, then that explains gravity. But I think, and I want to show that it is much less exciting, and that these values for length, mass and time are actually variables that exist in these equations, and I'll show you what they are. If you take the length, or the distance between two bodies, we'll say G, then that we call that R. That would be R cubed, which is the length cubed that's in the definition of G from a dimensional point of view. Then the mass of the Earth would be under here, and this would be what I've referred to in other writings as and videos as the period, the time of the pair of bodies. So if this were the Earth and the Sun, this would be the distance between the Earth and the Sun in a circular orbit, divided by the mass of the Earth, and divided again by the period, which in the case of right now, the period in cycles for the Moon is 27.3 days. But this would be in radians or days or hours or seconds per radian, not per cycle, because nature does not work in cycles, as Planck's constant shows, because that had to be corrected multiplied by 2 pi to make it radians instead of cycles. So this actually looked to me like an explanation, and in that chart you'll show that I do take these values not only for the Moon and the Earth but also for all the planets, and took the distance between the planets and the Sun, or Moon and the Earth, and divided them by the mass of the Earth, or the mass of the Sun in the case of the planets, and then divided again by the square of the period, and they all come out to very close, once you've corrected it to meter, kilogram, second units, they come out to 6.67 times 10 to the minus 11, which is the value that you get for G. And they came out extremely accurate. I was very surprised. They're all within about 1%, and the Earth and the Moon, which we know most about, came out actually much better than that. They came out, I think it was to 4 significant digits, the same value exactly as we use for G. So that, I think, confirms that G is not a natural constant at all. It is simply a function, a parameter, a summary that happens to be constant when bodies are in circular orbits. So that you take all the planets, and I'm sure you could do this with any orbital system in the universe, and find that if you put these figures in, you get the same value for G. It so happens that it's a constant. I don't think it's good fortune. I think it's a natural as a natural basis, but the numbers, the actual values, come from these human units. Now, let's now just see what that means, because if that is so, we can do some extraordinarily interesting, take some samples and look at them. For example, if we take G as equal to that, R cubed over m t minus 2, and from that we put that into the Newton's equation, we find that acceleration is equal to, as he put it, mg over r squared, and we often wonder where that square law comes from. But if we now replace G with this, we get this. We get that the acceleration is equal to the mass of the Earth divided by the radius of the orbit, and now G we're going to replace with r cubed divided by the mass of the central body again, and multiplied by the period squared. And you see that the mass cancelled out, and this answers the question I've raised before, and that is, why do we have only one mass in the equation for acceleration? We have two in the equation for force. Both bodies affect the acceleration just as both bodies affect the force. And this actually, the answer to that question is that that our equation for acceleration is like our equation for kinetic energy, half mv squared, with only one mass. And they're both true only when the body of reference, the central body, is very, very much more massive than the body we're considering. If the bodies are not in that relationship, then you have to have both masses in there, because they're both actually then orbiting their center of mass. When bodies orbit, it isn't one orbiting the other, they're both orbiting their combined center of mass. Now if you now cancel those out, make that just plain r, you get r over t squared, which is interesting. It says the acceleration is proportional to the radius. In other words, the acceleration increases with the radius, and that's interesting because that's what I found with my study of gravity, that where a body is moving in the same system with the same period, not different, not a comparison of different orbits, but the same two bodies, but moving more toward or away from one another, and a constant period, the acceleration actually increases as you get closer, which is as you get further away, which is surprising. But there's not something else you can do too, and that is that you can take two of these r's and the two of these r's and those two, and that is the radius squared divided by the period gives you the velocity. So this is equal then to the velocity squared, and then that r cancels out one of these r's and makes this r, and the m has already been cancelled out. So we've now got something very interesting, that the acceleration in between the moon and the earth is equal to v squared over r. You've seen that before, because that is the equation for centrifugal force, and it's that you're really looking at when you calculate using Newton's equation for acceleration. You're actually using this, and I presume he was aware of it, but he may not have been. But really, what gives the value of gravity what gives gravity its value is that gravity is the reaction to centrifugal force, and therefore exactly equal to it. And that answers the question as to where the inverse square law comes from, because the centrifugal force is inversely proportional to the square of the distance. So that's what we learned from that, and I'll go into more detail in a later video. Thank you for watching.